Hi again, John Hauer here. Recently, I was invited to speak at the 3D Printing for Industrial Applications conference that was held in Atlanta and hosted by Smithers Pira. My session was on the economics of 3D printing for industrial applications. Several of the attendees asked me for the slides, so I thought I would put together this video walking you through the presentation. For those that don't know, I spent about 20 years in the 2D printing industry before getting into the 3D space. I worked for Xerox twice and several large commercial printing companies. Primarily, I was responsible for selling equipment and helping customers simplify their workflows by building and implementing web-to-print e-commerce solutions. In 2012, I attended Graph Expo, the US's largest 2D print show. At the time, it seemed the writing was on the wall. Books, magazines, direct mail, and other forms of print were all dying. I started a blog called 3D for Printers and began evangelizing 3D printing to 2D printing companies. It culminated with an article I wrote for TechCrunch about why 2D printing and 3D printing really are a lot alike. Some fellow Cincinnatians saw it and convinced me to join them in starting 3DLT. It started as the market's first for-pay file marketplace, but quickly evolved to become a platform for 3D printing as a service, helping global retailers like Amazon, Walmart, Sears, and others sell 3D printed products online and in store. I exited that business in 2015 to form Get3DSmart, which is a consultancy that helps companies identify and capitalize on big opportunities in 3D printing. Before we dive into the economics of 3D printing in the industrial world, I thought I would give you a brief overview of the market. When it comes to 3D printing, there are opportunities in nearly every market. Most consider the big four to be medical, automotive, aerospace, and consumer products, but I can make a case for others like construction, oil and gas, education, and retail, among many others. 3D printing started primarily as a tool for rapid prototyping. It also has many other uses. In the next few years, the market is likely to grow significantly. Smithers Pira projects it could reach $50 billion by 2025. A few years ago, McKinsey forecasted that the economic impact from 3D printing could reach as much as $500 billion by then. Not only does this include direct revenue, but also all the ancillary steps like packaging. In their report, McKinsey suggested that as much as 5 to 10% of all consumer products could be 3D printed by then. Consumer products are a multi-trillion-dollar industry. If they're right, and even 5% are digitally manufactured, it's easy to see how 3D printing could be that big. Products are typically developed in a circular way. First, they're ideated, and those concepts are tested. Then prototypes are built, and they're tested until the product is deemed ready for mass production. While that is in the works, major decisions are made around supply chain, where the product will be made, how it will be packaged and shipped, where it will be inventoried, and how it will be sold to customers. Once it is in the market, companies typically support it, helping their channels sell, train, and maintain their products. As I mentioned, while 3D printing was initially for prototyping, there are many other applications, including jigs, dies, and other tools used in mass production. But if McKinsey and others are to be believed, those use cases could be dwarfed by opportunities with short-run production. At the end of the life cycle, there is also significant potential with spare parts and customization of mass-produced products. Sculpteo, which is a large online 3D printing service bureau, also conducts research on how 3D printing is used. Each year they do a survey and recently announced the results for 2017. Among other things, they asked over 900 3D printing users about their uses of the technology. While over 50% said they are using it for prototyping and proof of concept, 22% said they are currently using it for production. Another 16% said they use it for customization. What I also find interesting is that 10% said they are using it for marketing samples. The ad specialties business, also known as the promotional products industry, is itself a $20 billion industry. Could it be an untapped market for 3D printing? Also in the study, users were asked about their investments in 3D printing. 49% said they had increased expenditures in 2017, and 72% said they plan to spend even more in 2018. When asked what could have the biggest impact on future growth, most said that declining cost was the biggest factor. Before we dive too deep into the factors that drive cost, we should look at how volume impacts the product lifecycle. For successful products, it typically acts like a bell curve. At the beginning, when demand is unknown, order quantities are typically as low as possible. As demand takes off, quantities grow. Towards the end of the life cycle, they diminish again. At the beginning of the life cycle, digital technologies like 3D printing can play a huge role in helping these products get to market. At the end, when there's still some demand, but not enough to justify ongoing production, digital can once again play a role. But it's important to understand the concept of break-even, the point at which it makes sense to switch from one method to another. For any given product, the break-even is always an exact number. But as digital technology gets faster, more productive, and less expensive, the break-even moves inward. Consider 2D printing for a moment. When digital color first became available, it was slow and expensive. For a given product, the break-even might have been 50 units. But soon it got better and faster, and the break-even went to 500, and then 5,000, and then 50,000 units. With some products, high-volume digital presses can now compete at runs of 500,000 or more. For many 2D printed products, this eliminates the need for analog production entirely. Recently, I was shown a 3D printed part which may achieve the same. It is very inventive and will have widespread use in both business and consumer markets. It's also optimized for 3D printing and will likely never be produced using analog technology. Now let's talk about some of the elements that define the cost of 3D printing. The iceberg model can be a useful tool in helping visualize cost. It's estimated that up to 90% or more of the volume of an iceberg is below the surface of the water. With 3D printing, many people factor the costs of machine and materials, but there are many other costs lurking just below the surface. They may neglect to factor many other types of technology, including hardware and software needed to support not only production, but also other areas of the business. Sometimes they'll factor direct labor, but often others like management, operations, accounting, and HR are considered a sunk cost. Further, there is significant cost in process. This is often described as a transaction cost or the amount it costs to move an order through a facility. This one is especially important. A transaction cost of $150 might be justifiable if the average order size is $1,500. But what if the average order is $150? As short-run production plays a bigger role, that's a realistic scenario. Also in 3D printing, you'll hear people say things like, the cost of complexity is free, or the unit cost is flat. That's not exactly true. Say the price per part is $10. If the transaction cost is $10, the cost of one unit is actually $20. The cost of 10 units is $11 each, and the cost of 100 units is $10.10. By the way, a $10 transaction cost requires significant automation and is not easy to attain. A while back, I was approached by a person who was looking to sell his 3D printing service bureau. He was generating revenue, but was losing money. When I asked about his cost, he struggled to provide direct, fact-based numbers. We went through an exercise to identify his total cost of ownership. We analyzed all aspects, including the money he was spending to educate his customers, the amount he spent on software, his hardware and service costs, and the amount he was spending on materials. We also looked at his direct and indirect labor cost, the cost to run his facility, and calculated all of the soft costs involved in running his shop. His costs were much higher than he anticipated. Now, whenever these kinds of studies are conducted, you have to make some assumptions, most important of which is volume. The more cubic inches of material you run, the more fixed costs can be spread out. It became obvious that he needed to grow his volume or reduce his fixed costs. At that time, I was buying FDM and SLS, two of his biggest revenue generators, at about $15 a cubic inch. Others in the market had a cost of $9 to $12 per cubic inch and could sell it to me at that price profitably. Without significant changes, there was no way for him to compete. For these reasons, I believe that any conversation about the economics of 3D printing must begin and end with total cost of ownership. Okay, so enough about cost. Let's look at some of the factors that are likely to drive growth within the 3D printing industry. As I've mentioned before, the quality, speed, and productivity of 3D printing must improve for the market to grow. That doesn't necessarily mean that the machines themselves must be cheap. Would you rather have a $500 machine that generates $1,000 a month in revenue, or a $500,000 machine that generates $100,000 per month? The answer depends on a lot of other factors, but typically more expensive machines can generate far more revenue if you have the volume to support them. Consider HP's new multi-jet fusion 3D printers. They're not cheap, but were designed to be highly productive. Last year, when I was invited to Barcelona to see them firsthand, I expected to see one machine. Instead, they showed us a system using multiple machines. Jobs are built in one place, printed in another, and finished in another. In a production environment, the effect is amplified. While some jobs are processing, others are printing, and still others are cooling. It's a big part of why HP believes it can achieve 10 times the productivity of other 3D printing methods at half the cost. HP isn't alone. Plenty of other manufacturers are rethinking the way they design their equipment to achieve maximum productivity. Most aren't focused on the cost of the device. They're focused on the cost of output. Materials also play an important role. In the total cost of ownership slide I showed earlier, they made up 25 to 40% of the fully burdened cost. Driving those numbers down is key to the growth of this industry. But it's also important to magnify the types of materials that can be 3D printed. The Senval database, which is a comprehensive list of 3D printing machines and substrates, currently lists over 1,100 materials that can be 3D printed. Mass manufacturing offers many more choices. Part of the solution involves getting big chemical companies involved. They have the expertise in materials science and the scale to get new materials to market quickly. They can also drive volume, reducing cost. Fortunately, this is starting to happen and will ultimately lead to lower cost and more choice. But in the here and now, perhaps the most important opportunity resides in workflow. It's key to driving out transaction cost as well as other soft expenses. As new customers enter the market, a vast amount of time must be spent on education. Tools that help users determine cost and submit jobs will be key to growth. When digital printing first hit the scene, very little of it was ordered online. Today, over 50% of all 2D print is ordered that way. It drove a significant amount of transaction cost out of the equation. At the same time, it made it easier for customers to order only what they needed when they needed it. Web to 3D print provides other important benefits. It provides customers with an easy way to manage their assets. It also helps them make smarter decisions about where jobs are printed. Finally, it gives organizations a way to track what was ordered and by whom. Finally, it is impossible to understate the importance of killer applications. In the 2D industry, software manuals, healthcare benefits booklets, and digital photos drove the sale of a lot of hardware. Similar veins of gold need to be uncovered in 3D. For example, back in late 2015, VW was caught cheating on how it measured emissions for its diesel cars. Soon after, they announced a fix that was part software and part hardware. The part they announced was called a fuel regulator. The version they demonstrated in the video was in fact 3D printed. At that time, I suggested a radical approach. Instead of mass manufacturing the part and shipping it to thousands of dealers around the globe, I suggested they install 3D printers at each location and print the part locally. Would it have been more expensive? Certainly, but it could have eliminated much of the supply chain cost and demonstrated Volkswagen's commitment to further innovation. Further, it could have created a new revenue center for dealers, allowing them to print all kinds of parts, including those for competitive brands and classic cars. It might even allow them to cross categories, selling parts for motorcycles, boats, trucks, and construction equipment, among others. It's just one example, and maybe not perfect, but killer applications must be identified and reduced to practice. Finally, I'll end the presentation with a slide I often use to describe the speed of innovation. A few short years ago, 3D printing was an uncommon way to manufacture hearing aids. Then, over the course of only 500 days, the entire industry changed. Now, there are no companies who don't use the technology. Disruption happens quickly. You're either the steamroller or you're the pavement. Companies that don't lead are most likely to fail. That's it for my presentation. As usual, I appreciate your likes, comments, and shares. If you have questions or want to discuss in further detail, I encourage you to connect. And again, thanks for your time today.